Okay, good afternoon, everyone. First, I would like to welcome you to the Kent lecture. And Kent is made possible because of the donation that was made by Mr. Kent for the civil engineering department. Who was one of our graduates.
You're also in that meeting? Yeah. Yeah.
We'll mute everybody. So as you can see here, he has been working in civil engineering, and most importantly, he's the person that he established the Civil Engineering Alumni. And the Civil Engineering Alumni Association now is the largest civil engineering alumni association in the United States. So we give him a credit for that. He has been working as a civil engineer in civic organizations, as well as he has his own contracting business. So would like just to acknowledge the support that he has been providing for us in order to invite the Kent speakers throughout the year. So during the life of the Kent, which has been established almost 20 years ago since I came in, and we were doing it as a distinguished speaker only. With time, we changed it to a series of lectures. And one of the things that during, for example, just before COVID, we had the Around the World series where we invited people from different countries during the summer. It was very, very successful. And right now we try to have a theme for each semester, and we invite speakers from different universities from the United States as well as outside the United States, and also some of the students here, but also would like to always start with one of our distinguished faculty to kick the Kent seminars. So we did have some seminars about the sustainable mobility, modeling and mechanics and artificial intelligence. And this year we had it, or this semester we have it about electrification and charging of the transportation. So we have already except one defined for the speakers of this semester. So you can look at the program. As you can see, we have an outstanding program that involves people from the academia, from the industry, as well as from the government. So you will have a very good idea about what's going on in this space. And with that, I don't want to take too much, so I wanted to go ahead and start introducing our speaker, but this is the time. And we have all the speakers here. This is for the people who are taking this as a class, it's a mandatory. Other people, they can take it as a zero. And there will be a very, very small request that you choose a topic and you write kind of like a small report about that topic. So this is something for you, I guess, to just get educated about different areas during your stay here at the University of Illinois in different themes. So with that, let me go ahead and introduce our distinguished speaker today, Dr. Lehe, who has been here with us for 5 years, close to 5 years. And he's our economic bureau. So he completed his master's leads in economics. And after that, he went to Berkeley, where he finished or completed his master's in civil engineering, as well as his PhD with emphasis in economics. And it happens that he has the same advisor as Professor Oyang sitting in the back. I don't know if that's good or bad. What do you think?
A lot of professors have this.
Okay. So with that, we're really excited to have Professor Lehe with us here, and the floor is yours. Please join me to welcome him. Now, why are you now?
So, can you hide the slides before you? Thank you.
Okay, okay.
There, yeah. Okay, I am presenting on this presentation called AI for Cities and Transportation. It's totally different than my normal research, which is usually theoretical, stuff about economics, like Dr. Al-Qadi was talking about. This is actually totally out of my wheelhouse, new stuff. we're using AI for these two different purposes, and we're not gonna go too deep into the theory here, but I'm just gonna demonstrate these applications of AI basically that we've been working on in my group. So I have two different applications. The one is deep learning, and we're using it to measure parking lots and to draw outlines around parking lots. The other one, LLMs, we're basically the goal is to make transit data more accessible. We basically make a chat bot where you can ask it questions about a transit agency and it will respond, hopefully accurately. And then at the end, I'm gonna do a switch out of this. I'm gonna go to a little demonstration of the chat bot, right? Okay, so these are two different types of research that are kind of, they're both AI, but they're using totally different techniques. So the first, we'll start off with the parking lots, right? So some background. So why did we think of this? There's this policy that exists all across the United States called a minimum parking requirement. And it basically is, in a nutshell, it requires it's regulations that make developers build a lot of parking when you build a new building, right? So a lot of cities and states right now are relaxing these. They're getting rid of them or they're lessening them because a lot of our cities, as we'll see, are consumed by this parking. It makes it more expensive to build housing. For our purposes, it's not really important why they're doing it, but you can see, so I just did Google News search this morning, and just like in the last week, this is a big time trend. They're getting rid of all of these parking requirements all across the United States. So this is like the state of Montana, many cities in Texas, Colorado. So it's all over the United States and it's a big trend, right? So whenever this happens, there's sort of a debate about it, right? And so one of the things that people muster in this debate is these maps that show how much of a city is consumed by parking. And these are created by a group called the Parking Reform Network, who basically go by hand and draw outlines around all the parking spaces and parking lots in a downtown area. So this is Atlanta. And then there's just some other cities. There's Kansas City. You can see that there's a lot of our downtown areas are very consumed by parking. You can see this, right? So these are just 4 cities that are kind of nearby us. I can't remember, I don't have the Chicago one though. But yeah, in all these cities, it's about a quarter of the land downtown is off-street parking, right? So this is not counting the on-street parking or the roads or anything. So we have quite a lot of parking in the United States. Many would say too much. So it turns out that people really love these maps, right? So if you go search, journalists will use these maps in a lot of different news articles, but also if you go to like a city council meeting where they're debating this, they'll use these maps too, because a lot of people just don't really realize how much of their city, like a third of the downtown, is taken up by parking. So and there's also a lot of attempts to estimate overall how much parking is there in America. That's attempted by statistical inference, right? They sort of have some statistical way that they believe they can try to figure it out. So the thing is, these maps are very hard to make. So they only exist for small areas. So this is the city that I'm from, Birmingham, Alabama. It's a huge city, but they only have mapped this tiny little area, right? And that's for an obvious reason, that it's very difficult. You have to go by hand and like draw park outlines around everything using a satellite image or maybe some other statistics. So you can't really measure very many places efficiently. And moreover, you can't really get statistics. So like I said, there's a lot of statistics that are out there, especially in city planning, that's saying, oh, the amount of parking in the United States is as big as the state of Connecticut or the state of sometimes Massachusetts, things like this. But the truth is that we don't really know. And if you look up these estimates, they will vary quite a bit. They're all large numbers, but they vary a lot because they're statistically inferred. Whereas if we had something like this, we would just kind of know. We would just like add it all up. This is direct measurement rather than inference. Okay, so enter semantic segmentation. I'm not going to go too deep into the deep learning kind of aspect of this, but essentially in a nutshell, semantic segmentation is a type of process that will look at an image and divide it up into objects, right? So other types of deep learning might be focused on object detection, right? You might show a picture of a duck, says this is a duck, this is a picture of a computer or something. Semantic segmentation is about dividing up an image into different objects, right? So here you have the cars, sidewalk, roads, people, traffic signals, etc. So this is a kind of an obvious use case for semantic segmentation, that if we could take satellite images, like the kind on Google Maps and the kind that you use in your navigation apps, and we could teach a model, we could train a model that could accurately draw boundaries around all the parking lots, off-street surface parking lots, then we could actually directly measure these, could automatically produce these maps. It would just be very efficient. We could get good statistics. And at the end, I'll talk about some other applications. So there's some big challenges here, right? So if we look at a pair of parking lots that we've done by hand, so some of the challenges would be that they have kind of unusual shapes, right? There's a lot of little like divots and such around them. Also, parking is almost always surrounded by trees or bushes and such, right? Sometimes they cover up some of the parking in the image. Other times they cast shadows depending on the time of day that the image was taken, that the satellite image was taken. They, in different parts of the country, also colors. You don't think about it. I mean, I guess actually a lot of people in this room do think about it. But in different parts of the country, pavement is made out of different stuff and is a different color, right? So, for example, we pulled up Meridian, Mississippi. All their pavement is red, right? It's also true for part of Wisconsin. I'm not sure why. So different places, it's a different color. The vegetation varies. So we have data from Anaheim, California, where there's really not very much vegetation, or Phoenix, Arizona. Then you go to like Portland, where there's trees everywhere. So it's pretty challenging, actually. So some people ask, okay, what about OpenStreetMap data, right? If you're familiar, it's an open source data set where people have just volunteers have tagged things. And this is a great starting point, but it's not actually a substitute for what we're trying to do. It's full of errors. So here's an example of an error. This is where you can see, this is from OpenStreetMap. There used to be a building here, obviously, right? But now there's not a building anymore. They leveled it and they turned it into a parking lot. So this is a true one. The other thing about OpenStreetMaps for training a deep learning model is that you have to think like the computer model, right? So if I'm going to teach a computer model to identify things, the computer model doesn't know about the idea of a parcel or a block or anything like that. It knows surface. Is this surface parking, right? So if you see here, the volunteer has drawn the boundary of this parking lot in OpenStreetMap, but they've included the area around it. They've gone to the edge of the lot, right? If you give this to a computer, it will not learn very well, because the signal here, you see that it's including a bunch of bushes along the edge. You need it drawn directly along the edge of the pavement. Does that make sense? Because you're trying to teach it to pick up cues. It can't possibly pick up the intuitive cue of like, oh, this is what a parking lot looks like. It's going to have to pick up the cue of this is what the edge of pavement looks like. These data sets also count garages. We aren't counting garages because you can't tell that in satellite data, unless they have a parking lot on top of them. Okay, so the training data set, we have to annotate all this stuff. So what we did was we started out with two data sets. One is the downtowns that the Parking Reform Network had already done, the OpenStreetMap data for a series of cities, including Champaign, Anaheim, Lubbock, Texas. We kind of randomly picked cities. Then we correct all these, right? So we have all these tiles. And then we get the tiles from Google Maps. They're to 30 centimeter resolution. Thank you to the REU program for funding the students that did that manually. So we wound up with this training data set. It has about 30,000 parking boundaries, about 10,000 or 11,000 image mask pairs. So what I mean by an image mask pair is this is a tile that we downloaded from Google Maps. This is the corrected image mask, right? So this is telling me where all the pavement is, where all the parking is. And then this is when you put them together, you can see the parking is outlined, right? Okay, so we have a data set of 11,000 of these pairs, right? And it gets bigger actually all the time. Okay, so here is another enrichment that we did. So we have the RGB red, green, blue 3-channel. What we see from the data set from Google Maps, right? We went to the National Agricultural Imagery Program, right? And they have these images that are enriched with a near infrared channel. Near infrared is something that we can't see, but a computer can see it. It's basically the spectrum, the part of the spectrum that plants emit, right, when they're green, right? So this is very useful for our purposes because because parking lots are almost always surrounded by grass, right? So actually it provides a contrast. It really makes the edge of the parking lot stand out. If a parking lot is surrounded by grass, normally, depending on if the grass is really standing out in that image, you might not see it, or if there's a shadow or something. So here you can see they're much better. The problem is that this is a 1 meter resolution, whereas the Google Maps is 30 meters. So we had to scale it up and interpolate it, right? And it happened that when we did that, it turned out to be very accurate still, and all the boundaries were maintained. So even if it looks kind of fuzzy, what we're really concerned with are these borders, and it maintains those. Okay, so the whole training phase is basically we build the data set. We train it on a deep learning model. We try out three or four different popular models. Then we use it to predict it trains itself on that. Then we have this inference block. So we kind of make these predictions. Then we convert it all in the end after we make the predictions to GeoJSON geometry polygons. Once it's in GeoJSON format, so that's basically a bunch of lat longs for every single parking lot. We have a little shape, right? Then we do post-processing, which we clean it up. We have the computer clean it up to make it more accurate, to make it better. Okay, so post-processing, here's some steps, right? So this has a hole in it. You can see there's a hole. This happens all the time. Parking lots do have little islands in them, right? Pieces of grass, but the deep learning model isn't good with 11,000. We probably need like 200,000 or more before we really stop getting things like that. But we can identify these holes easily because they're just very small, oddly shaped things, right? So we have a post-processing step that does that. And the other thing that we end up with are these little islands, right? Where it randomly thinks that there's some tiny piece of parking out in the middle of nowhere, right? Well, a parking lot is not going to be, it's not going to be smaller than a certain area. It might not have a certain shape. So you can automatically eliminate these. The more you eliminate these, though, the more error the more like you get rid of your false positives, the more you're going to get false negatives too. So there's a trade-off there. And then finally, we simplify the edges. This isn't a great example of our predictions being accurate, but it is a good example of the simplification. So after it comes out of the GeoJSON, you can see the vertices. That's what these red dots are. These vertices are there's thousands of vertices for this tiny parking lot, right? Because it's very curvy. In real life, a parking lot is not a very complex shape typically. And moreover, we are actually trying to create things that potentially people like the Parking Reform Network or somebody like that could sort of correct if they want to. And so it's much easier to correct it if it only has a handful of vertices versus if it has thousands, right? So actually building our training data set gets faster and faster because as the model gets better, it makes a better prediction. And then we have somebody correct it. Right now it's a new student, Tanvir, and we can correct it easily. And then that's more training data, right? So it's kind of accelerates. Okay, the last stage in the post-processing is removing, no, there's another stage. We remove buildings, right? So it has so the tops of buildings and satellites look a lot like parking lots, right? So fortunately, Microsoft has a building footprint data set. So for example, this is our first guess, and you can see that it guesses that all of that is parking, but it's really not. The red part though is the Microsoft building footprint data set. So we just go in and we subtract out all of the building footprints, right? And this leads to obviously a massive increase in our accuracy. So this is before subtracting the building footprints and then after, right? And you can kind of stagger these you can do the post-processing step more than once. Okay, so then and then the last one is that we use OpenStreetMaps. OpenStreetMaps has the databases of all of the roads and highways in America with lots of information about them, like how many lanes they have, sometimes what their width is, etc. So here's a case where this happens a lot. You've got two parking lots across the street from each other, right? So and they're the same color as the road. So in this case, the model thought it was just one big parking lot, right? But if you come in here and if you remove if you remove the street, you're going to get more accurate, right? So then that's sort of the last stage, right? Okay, so then results, right? So what we've looked at so far is actually sort of more accurate than it seems by looking at these images that I've shown because I'm focused there on showing the mistakes and how things get fixed. But if we go through all of the steps, you can see these are two different measures of accuracy that are used for semantic segmentation. So actually for the segformer model, we get up to, for this MIOU, we get up to 79.4%, which we consider to be very high. And whenever we've shown it to deep learning people, they thought, wow, that's a very good one. And then for this PW metric, it's 92%. These are just different metrics that I don't have time to explain today. But we would really like to expand our data set 10 times or something and try to get these up to the point that it looks almost like manually generated. These are just results for different models. And is this Champaign, Sharon?
No,
What is
Portland.
This is Portland? Okay, this is Portland, Oregon. Yeah, you can see here that this is the ground truth. All three models at a scale roughly look like the ground truth. But if you zoom in, you can see that the this is a little box that we want you to focus on. There's the ground truth. If you go look at the segformer one, you can see that's the closest to the ground truth. DeepLab v3 way overestimates things. So does FCN, but segformer does a very good job here. Okay, so then the plans for the future is we want to like 10x the training data. So we have like I talked about an accelerating process. So we have the model produces predictions, somebody manually corrects them. And then when they manually correct them, that's more training data, which goes back into the model and just kind of like loops around and gets faster and faster because this step, the manual correction, gets faster and faster. It takes less and less time to do a tile. When we started this out, it would be like take like a week to do a tile. Now we can do one in a few hours because there's just not very many mistakes. Okay, that said, now we're going to move into a completely different application that just also involves AI. Okay, so we have this goal of creating a chatbot that answers questions about transit, right? So this is, you can learn a lot about transit, obviously, if you download the transit data and analyze it yourself, right? So that's the best way to learn about transit data, is to analyze it yourself. But imagine, try to imagine just something that you could talk to. Like a lot of people have a friend that knows a lot about the transit system where they live, or you move to a new city and they say, oh yeah, you want to go there, you can take this, right? You can take that, right? There's a lot of people should sort of rely on somebody conversationally, even though we can go on Google Maps or the website. If you want to ask people questions, this is like what we have in mind is like a friend that knows a lot about the transit system. So you can imagine kind of stop questions that an ordinary person might ask, like, what's the closest stop to my house? What's the last bus on my street? How long does it take the bus to go from my corner to my workplace? How many times does the bus stop on Green Street? So we have like a lot of questions, right? You just might also be curious about the system itself and say, like, what's the longest route in the system, right? So these are all different types of questions. So fortunately, these are answerable because there exists, if you're not familiar with transit, the world of transit data, it's one of the best data sets that probably exists because it's used by private companies all the time, right? So when you go to Google Maps and such, they're using what's called GTFS data, General Transit Feed Specification data. So all the transit agencies in the United States, Canada, and most countries, they publish all of their data as a standardized format. This is just a picture of it. You don't have to memorize it, but a standardized way to represent transit data. So we don't have to deal with the fact that all the different systems are storing it in their own Excel files or something. They store it all in a standardized way. They upload it onto a particular URL that is public and that is in a database so everybody knows it, right? So this is a very popular way. So because this is so well structured and it's fairly accurate, actually me and my student Praneeth that did this work, we wrote another paper earlier this year that's just called a survey of errors in GTFS. We were looking at what are the types of errors. And there were very few errors, and the ones that exist today are not very substantial. So actually this data is pretty reliable. Another thing that we learned in an earlier paper that was published earlier this year is that the popular LLMs like GPT-4, Chat-GPT, GPT-4, Claude, Sonnet, these popular LLMs, they actually know a lot about GTFS already. That's to say they don't know a lot about GTFS data because they don't have data sets inside of them, but they know a lot about how GTFS works. So you can ask them a bunch of questions about GTFS. You can say, oh, where would I find the time that the bus comes to my stop, right? And it would give you a correct answer. So the LLMs, because the LLMs have all been trained on the documentation of GTFS, which is online, so they're all actually pretty savvy about it. I mean, more than you would think. And actually, we did these tests last summer, and since then, all the LLMs are like twice as smart, so they do a very good job. Here's an example of one of the questions that we asked. So we say, like, can a GTFS feed contain multiple agency information? And it gets the right answer. Okay, so when we do these, we made a benchmark, and there were some of them that they were very good at, like defining things, categorical mapping, they weren't as good at, but overall they're pretty accurate. Like for different parts of our benchmark, 70, 80%. And this was, like I said, like a year ago, so now they're actually much better. Let me turn that on. Is that Okay. So it can generate code, right? So code is what you need in order to actually read a GTFS file, right? Okay, so essentially what we do is we create an interface called GTFS to code that accepts a question. It asks an LLM, such as Claude Sonnet, GPT 4.0, GPT 4.0 Mini, Llama. It asks these LLMs to generate code that answers that question. Then it runs the code on a remote server that we have running. So it's called a Streamlit app. So there's a little server. So it runs the code that the LLM generated, and then it gets the result from that. And then it uses that result, the code result, in order to generate an answer to your question, right? So does that make sense? So we're using an LLM to generate code, and then we're running that code. And when we run that code, it's on a server where we've already uploaded the transit data to it. So just to be clear, it is impossible for the LLMs to know very much about your system if you don't have the GTFS file. You can go on there right now and ask it questions, but it will just be answering based on like, somebody wrote a blog post one time about how the subway ends at midnight or something, right? It doesn't actually have any access to transit data. The LLMs also do not really run code. If you go to Chat-GPT, right now there's like a little Python terminal that it will run for like short snippets of code. We're talking about like big computations that involve reading in data and performing big calculations. They won't do that, right? So this is a substitute for using those directly, even though if you go actually ask them right now, it will get some questions right just because somebody wrote about it on the internet one time, right? Okay, so then we create this web app that I'll show you in a second. So it has a little interface, GTFS to code. You can select your agency. We have like 10 on there. You can select what LLM you want to generate the code. So how does this work? Yeah, okay, so then, so this is an example. Find the stops at Illinois Terminal. This is the result. So it tells us there's 3 stops at Illinois Terminal. There's the A, B, and C, right? There's actually, if you go down to Illinois Terminal, there's these 3 stops. So then you can click on this and you can actually see the code that it used to generate that answer. And then you can also see the code evaluation result, which is useful because this evaluation result is used to produce this sort of natural language answer. And then it also has visualization capabilities. So it just kind of tries to throw a little bit of, it's almost like a waiter or something. Like it just tries to have nice service to you. So it'll just create a map for you or create a pie chart or something, depending on what your question is. It's a little bit hard to tell exactly what kind of extra stuff it'll do. It has those visualization capabilities that are, we can draw maps, you can have like bar charts, all kinds of code. Okay, so how do we make the LLM write correct code, right? So also, if you go to ChatGPT right now, or Claude especially, and you ask it, hey, I have a GTFS file on my computer, I want to write code that tells me, what's the longest route, right, in the CUMTD system, right? It will generate code, right? It may or may not work, right? So the problem is, especially as it gets more specialized, your question gets more unusual, it probably won't work, right? It might hallucinate things. So for example, it might be like, open the routes.txt file and look at the length column, which doesn't really exist, right? So there's all kinds of hallucinations, and the basic ones, they do okay job. It also won't run the code for you. So what we do is that we basically, whenever you talk to an LLM, behind the scenes, you can pass it, if you use the API, you can pass it a huge prompt, right? Actually, a lot of text that goes before anybody asks a question. And what this text does is it sets up the LLM to play a role and to know certain facts, right? So you might say, you might have like if you were making a website for a toy store, right? You might have like a little bot on there and you might say, our customers are going to be like 9 years old or younger. We're looking for things that are $30 or less. So when people come to you asking for recommendations, do that, right? So then, does that make sense? So you can prime the LLM to do stuff. Essentially what we do is that we create a huge prompt with a lot of priming and a lot of examples. So there's an example GTFS feed that like a very small network that's not real, but it gets the idea of how they look, what they look like. And then we use that before you ever ask a question so that the code it generates is actually workable a lot of the time. It doesn't work all the time, even with this. So here's an example. It's like, it starts out like you're an expert in GTFS and Python coding tasks, because the language that we generate the code for is Python. We give it some knowledge, like we say, like, okay, every file is in a pandas data frame object and the speed object, et cetera, et cetera. So we get it all set up to write this code that we can then run, and we give it information like, okay, the agency.txt file, it's part of GTFS standard, has these columns. This is a string, that's a string, that's a string. Other ones are floats, et cetera, like that. There's all kinds of stuff. So basically, as we train this thing, we're really just creating a more and more complicated system prompt to prime it. This is just more stuff like, yeah, as we use it, like we find it makes certain types of errors. Like the times are seconds since midnight. The date fields are already converted because it might not really understand that when it first generates its code. So overall, the architecture of the thing looks like this. You have a query, we send the query and the system prompt, that's an input. We send it to the LLM, let's say it's Claude, right there. Claude then produces code. We send it to our Python REPL, something that will run the code. The Python REPL takes the code, it reads in the GTFS data that we have already uploaded to the server. It produces code output, which goes to a different LLM. And that different LLM takes the code output, it's like a Python object, and produces something that's like we would consider an answer, like a verbal answer. Some main challenges: the transit agency sometimes makes errors in its GTFS file or has its own conventions, right? So an example would be CUMTD is a little bit confusing because it also supplies school buses, right? So school buses for our system are in the GTFS feed. Also, we like label different parts of our day as different routes, basically. So even though in your language it's just green, right? And to the way that they operate their service, there's like green hopper, regular green, green weekday, et cetera, right? Geocoding, so we rely on Google Maps for geocoding. Sometimes it's not very accurate. So for example, we noticed yesterday that if you ask it for this, like if I say the corner of University and Victor Street, it will do better than if I just say University and Victor, right? And if I say Street and Avenue, it does better, right? And sometimes if I reverse the order, it gets it wrong. Like if you say Victor Street and University, it doesn't know what you're talking about. And if you say University and Victor, it does. Something like that. So that geocoding is a challenge. And then, but the biggest fundamental challenge that you don't really think about until you sit down to do this is that the concepts that we use in our conversations are actually pretty vague, right? So if I said what buses stop at the terminal, I mean the Illinois terminal, right? I mean the only terminal, it's the only terminal that could be, but if I'm going to code this up, it's going to help if I say Illinois terminal. What time does the last green bus stop at Illinois Union? Intuitively, I know what you mean. You mean any of the green buses, right? But it doesn't know that these are all types of green bus. It means there's green hopper, green evening, green weekend, green Sunday, green late night, green alternate 1, there's green alternate 2. There's all these different greens, right? There's green east and west, etc., right? So it doesn't have that human type of intuition, really. I mean, it approaches it, but it's still not perfect, right? So this is really the biggest challenge. And this is probably where just a lot of work is necessary. So future work would include fine tuning, human in loop, so that it can sort of ask follow-up questions and stuff. Just working on to improve reliability and also improving the geocoding. Okay, thank you very much. So I wanted to finish with enough time. Do I have enough time to show some examples of it? Yeah, okay. All right, good. All right, so we're gonna pull up okay, so we have CUMTD pulled up here. CUMTD, unfortunately, is the least accurate one because of the issues that we were talking about. So if it doesn't work, we can switch over to SF Muni, which is a very good one. It's not like they're doing it wrong, they're just doing things in an unusual way. So I gave it this question and started out. It said, show all the stops within 300 meters of Newmark Civil Engineering Laboratory. And you can see there, it makes a little map and it drew that, right? So it wasn't primed to already answer that kind of question, right? It figured out what to do. So I could also ask it something like, what route has the highest frequency? We'll see if it gets that. So it's about 50-50 right now, or maybe a little bit better. And it also will take a second because we're using Claude, which is a fairly slow LLM. We need to put a timeout. Okay.
Yeah.
Oh, there it is, yeah. So it claims that the silver has the, no, that the Lehe limited Sunday. So here you go. This is the silver has it's claiming a 4-minute headway. So this is a good example. I don't think that's true, right? Okay, so I'll do a simpler one. Show all the stops on, let's say, University Avenue, or let's say Green Street. It has a lot of stops.
Can you zoom in a little bit?
Yeah.
Please. Thank you.
Go over to this. Yeah. This is the San Francisco system. Good. Okay, so. Yeah, so there we go. So yeah, it's made up that. So show all the stops on Market Street, get a map of all the stuff on Market Street. I might say, what is the longest route? Such a word. It's 91. Oh, and it prints out a map of it. So you can see there's the 91, right? So also you also see here though, like probably some facts about direction. So it's showing me both of the directions, right? But it also gives me like the information about it, like the length, it's 23 kilometers long, et cetera, like that, right? I can also say something like, if you go to San Francisco, you might go to Pier 39 where they have all that tourist stuff. What stops? This worked earlier. Or just like if you have a play, let's say Dolores Park, right? Yeah, there we go. Yeah, there we go. There's Dolores Park and there's all the stops there close. Good. Okay, so you get the idea, right? So it's obviously like a work in progress, so we haven't been working on it that long. But the idea is that eventually this would be something that could be used to enhance the accessibility of the transit system. So instead of having to go on Google Maps and type in something very specific, like I want to go from here to here, and then if you ever say I'm departing at 5 p.m. or something like that, you could actually just have more of a conversation partner that would actually walk you through doing everything about using the transit system. Or if you're just curious about your transit system, you could get questions like that. Okay, so that is the presentation. These are 2 applications of AI. I'm very excited about the future of AI for transportation, and I hope you are too.
Thank you for the nice presentation. I have 2 questions. One, with respect to this, maybe you answered already, but if I were more interested in the services, right? Hospital, grocery store, more so, I think this one is a park, which is a geographic like pin.
Yeah.
If it's services, will it also include that type of functionality?
Yeah, it might already do that. So like, let's say we were saying, show me all stops that are within 50 meters of a hospital. This might work, I don't know. It is very much like having a person, right, that is not very reliable. And it's not really, it doesn't feel like computer programming. It feels, it feels like advice.
Yeah, because I was more curious on a purpose-driven question than description of the stops or time.
Yeah,
Or
well,
I have a goal, can you help me reach this goal through going through the day?
that's the, that's sort of what I was talking, oh, okay, cool. So those ones, those are all the stops that are right next to the hospital, right? But at the end of the day, that is kind of the friction of, sometimes our questions are, we actually want to start a conversation rather than having a particular question. As right now, we're limited, we're not really having a back and forth with it. So we can't narrow down exactly what you would like right now, but in the future, we'd like to have that by having some sort of follow-up questions or things like that, right?
So second question, for the first word, how do you remove necessary access points? So for instance, like for freight parking, there's gonna be maneuvering area that you cannot add to the parking
yeah.
lots.
Yeah,
Data set, so how do you remove the ones that are actually parking lot versus the one or necessary area for movement of?
yeah, that's a good question. So we basically, it's a judgment call, right? Like if there's a little road that drives to a parking lot, right? So imagine that there's a little driveway that goes to the parking lot. Do we count that or not? We only count it if it's very short, right? Like, so if it's, the parking lot is like directly next to the road or something. But if it's like a long, narrow road that goes out to a parking lot, then we don't count it, even though in a sense it has the purpose of accessing parking. We don't want it to start recognizing roads, right? So we try to be kind of pure to get it to learn. In a sense, like the goal is also limited by what the machine can easily do, right? So if we taught it to like do those kind of roads, it would start recognizing regular roads, yeah.
But I'm talking more of the area behind.
Oh, that's all gonna be parking. Yeah, it's all gonna be park. If it's contiguous with a parking lot, right? If it's just like, if there's like an unloading docks at a Walmart, that's all gonna be parking. Yeah.
Thank you again for your presentation. Regarding the first project, I would like to ask you, I understand you have to remove the streets for the vision to be more accurate and that you only have satellite images, but do you think, is there any way to include parking buildings or street parking using this technique?
Yeah, so if you wanted to add it, so that the machine learn, the deep learning is not gonna do that, right? So that's gonna be something you'd have to supplement it, the same way that we use that building footprints data set. That's a case where you might go into OpenStreetMaps and ask it for where are the parking garages, right? It will get a parking garage if it's on top of a building, right? If it's pavement that's on top of a building, especially with cars parked on it at the time of satellite images or painting, right? It will get that, right? But it's not going to be able to look at buildings and tell what their functions are, right? So that in order to produce the final data set, you definitely would want to enrich it with other data sources like that.
May I ask you a second little question for the second project?
Sure.
So how is this currently working? Have you uploaded all the GTFS files within the server?
So we have here for this little demo, I think we have like 10. So we have CMTD, DART, Dallas, San Francisco, Boston, what have AC Transit, Oakland. So yeah, we have these. Yeah.
Okay.
Yeah.
One possibility would be for street parking would be to supplement this with Google Street View images. That there you can find street parking and it's geocoded, so you can find kind of like if there's street parking. A question I have is, have you tried to segment anything that Facebook put out there? Like,
Yeah, we tried that. Here,
Does
you
it
wanna
work?
talk about it? Yeah.
Actually, not so good because it for the most of the times it even couldn't recognize the parking pavement. It tries to have the objects like cars or trees and those.
try putting the dots on the objects that you're trying to find.
Yes, I tried that, but it wasn't that good because yeah, I tried the grid form of that. But for most of the time, it just consider all the parkings as one object in an image. So it consider all the parts that has like the streets between, or it try to remove the cars from that. even though the cars are in parking.
Interesting. I have a question about this. So the LLMs are moving really fast, right?
Right.
And like a very good business opportunity for these companies is to get rid of all the data scientists that the companies hired by kind of like getting, kind of like digesting the data and being able to do analysis, right?
Right.
So what are the, have you thought about what happens, like you've done all of this and like what happens if, OpenAI comes up and say, okay, now we digest any sort of data set that we can provide you and now analyze the data and provide you answers. So, how this still becomes relevant in the events anything like that happens?
If they were to train an AI if OpenAI brought its resources to bear on the GTFS thing, they would solve it very badly. And yeah.
But I'm thinking about something more generic, like, is there anything unique about this particular application that would make it harder for it? Something like segment anything, like it's supposed to work on a lot of things very well, but it doesn't work for that particular application. Is there anything specific about this that would make it harder for a generic tool to solve it?
Well, part of it is in building it, we use the fact that we understand the GTFS format very well. So we know what all kinds of mistakes or unusual coding conventions different agencies have, right? And it's also like structured for a particular purpose. Like an example would be there's a column called shape distance traveled. It's like as you go along a route, it's going to tell you how many meters from the start of this trip is this stop, right? So like because we know like physically that it is a transit vehicle moving along, we know that number should be increasing. And we also know from our error surveys that it doesn't always increase. Sometimes it decreases because there's an error, right? So these are the types of things that are in the prompt. We already tell it to be aware of certain things. So if the question is like, can you plug it into a very generic thing? I think it would do a poor job. But if the question is, could AI solve this by like in 2 weeks? Yes, it would be amazing. Yeah. Yeah, they would just get somebody from a transit agency and they talk to them for a while and then it would be over and done with. So I think that maybe, in the end, what this shows is that I think actually it's demonstrating like a prospect of the future. Something like transit is actually still very difficult to use, right? So when I go to Chicago or something, I pull up my Google Maps, I try to use it. Sometimes I get confused about something. It's just kind of difficult to use, or if you're considering where to get an apartment, you want to be on a certain bus route, you have to like kind of go and then like type this in and, whereas if you had something that you could just, and especially when you get into people that probably might not be that literate, right? So there's a lot of people that have low technology literacy or just like low literacy overall. They might not really be able to use something like Google Maps. So I think that this does show the future of something like mass transit. There's a big barrier that you might not think about all the time, but it actually is very confusing to use mass transit a lot, especially if this could be linked up with real-time data that would be like an intelligent, omniscient friend, right? That would be telling you things all the time. Yeah, good question.
We have time for one more question.
Yeah, thanks, Louis. This is very interesting. And but first of all, I might suggest trying Apple. I think it's a lot more user friendly.
Okay,
That's also my personal bias. I do think it's a little more user friendly though for someone who knows less about transit.
Yeah.
But I guess I had a question actually about the first project you presented, and this is maybe very, very basic question, but in the motivation part, what's the reason that people actually want these maps? Is it to advocate for less parking? Am I understanding that right?
Yeah.
And what's the reason they want less parking?
Oh, because, well, I wouldn't say that they want less parking, but they want to get rid of these regulations, right? So they want to get rid of the regulations because they make it a lot more expensive to build housing. And it's impossible, like, so for example, if you go to a neighborhood like Campus Town, right? It's impossible, that doesn't have minimum parking requirements. It's impossible to build at that density with these parking requirements. So they want to enable those types of dense neighborhoods to be built again, like the kind that, America used to build like before the 60s. They're pretty much impossible to build with these parking requirements. So people that want to build these things, build more housing, etc., are pretty interested in this. And then in addition, I think this has more applications beyond that though, because just a data set of where all the parking is has uses that I can't imagine. Like I showed this to Professor Raisler, and he said, oh, you could use this as a classifier, and then you could figure out asphalt versus concrete parking lots, right? Or you could also, he also said you could use it for heat islands. So I have kind of the confidence that that this is useful for things beyond just this types of map things, although this is the original inspiration and the people here were very helpful with us and they want to use it when it's good. Then I hope that there's just some value in knowing where all the parking is and how much there is, yeah.
And you answered the second part that I was gonna ask, because I was gonna say, you could probably focus a lot more on urban features and train a much more exact model, because nobody's trying to build more housing in the Rantoul Walmart parking
Yeah,
lot, right?
yeah.
Sorry to those from city of Rantoul
Yeah.
online. But nobody's trying to build more housing there, right? But if you could probably very precisely train your model to identify parking that's in a very inconvenient location, right? And that would also help these
Yeah, in the dense area.
and yeah, that when these people go to make those arguments, they may actually even be able to match up, hey, these are your most egregious parking
Yeah,
spaces that are really could be better used. I feel like that would be a good use for kind of these activist type people, I would say.
yeah, that's probably true, yeah, if it was trained. I mean, we're very interested in urban areas in general, and pretty much all the off-street parking is either at malls, urban areas, or industrial sites. But we mainly focus on urban areas.
Thank you so much, Professor Lehe. Everyone,